Okay, we have the common ion effect, and determine the degree of ionization and the pH of a solution that is 1.5 molar acetic acid and 0.1 molar HCl. Okay, so we see this as a strong acid. This is going to produce nothing, 100% H3O plus when it goes into solution. So that's the common ion. Let me draw out for acetic acid. We have HA plus water goes to H3O plus. That's A minus. Now this is, let's do this out here. HA is 1.50. Now the concentration of H3O plus is 0.1 molar. That came from the HCl directly. So when you have a strong acid, it's going to give that, whatever its concentration is, that's what H3O plus is going to be. That's the ion that they share. That's why it's called the common ion effect. Minus X plus X plus X. 1.5 minus X. 0.1 plus X. And then X. So we solve it as X. 0.1 plus X. And there's a little trick here. I don't want to call it, I hate to call it a trick, but it is something that you have to be careful of. Now this is acetic acid, so its Ka is 1.7 times 10 to the minus 5. The approximation is going to hold. You can definitely check it. So it's going to be 1.75, 1.70 times 10 to the minus 5 times 1.5 divided by 0.1. And I put this one in there, especially because I see it in the book. Now this counts, and so it can come up on the exam. And even though it's in the book, if I didn't mention this, I'd feel kind of bad if I put it on the exam, because it's tricky. So this is 0.000255 molar. Now that's X. X is usually equal to H3O plus. But in this case, it's 0.1 plus this. So the concentration of H3O plus is 0.1 plus 0.000255, which is approximately equal to 0.1. It's going to round back to that. So our pH is going to be 1. If you put in the if you put in 0.000255, you'd end up with a pH that would be 3.59. And let me just draw a line here. The pH for 1.5 molar acetic acid alone, no H3O plus, no HCl in there. The pH is, I did this out. Where is it? 2.29. So if you did it out and you used this X, this term as your pH, you'd end up with a pH of 3.59, which would be greater than this. So you've added a strong acid and the pH went up. That doesn't make any sense. It's because we already have, the X is not the H3O plus, it's what's added to what we already have. So be careful of that. Now the degree of ionization, that is X over 1.5. So that's going to be 0.000255. Should have changed it over to scientific notation since we're using this now quite a bit. 0.00017. So much less than a percent. And let me see if I have it handy here where I can determine the degree of ionization with the, yeah, so this would be 0.005 divided by 1.5. So the degree of ionization in this case is 0.00333. So it's a small number, but it's still much larger than this. And that's what the common ion effect does. If you have something on this side, Le Chatelier's principle says that it should shift back to the left because of that, or it should have that part of an effect. It has to go forward because the reaction is going to take place, but it's going to be pushed back by this common ion. So the degree of ionization goes from about 1/3 of a percent down to, what would that be, 1/100th of a percent or a 50th of a percent. So it gets dropped away. Now that's a trickier one to see, and the main focus here is on that pH. So that's the one the student would say, that's a trick question. It's no longer a trick question because I've just shared the secret with you. So as long as you're doing these out, you should be fine. Okay, so determine the pH of a solution that is 1.5 molar benzoic acid, given here, and then 0.75 molar sodium benzoate. So we see that we have a salt and we have an acid, so we'll just call this HA, and then this is NaA, and we're really only going to be interested in the A-. So we can set up the problem as we normally would. Ice table, they gave us 1.5 molar. And then the A- comes from the salt. This breaks up 100%, so we have 0.75 molar here. Minus X, and this is 0, plus X, and then we solve as usual. The nice thing about these common ion problems, so the common ion here is that this benzoate is part of the acid and it's part of the sodium benzoate. So they both share the A-. And what I was going to say is that the nice thing about this is that the approximation will hold, and because it holds, that we can get rid of both x's, and the problem becomes much easier. The x above here, and then the x below. Now we just have to find. Now we're producing H3O plus, so it is an acidic. It's a Ka expression, so we can use the Ka for benzoate, and or for benzoic acid. When people see the salt, they say, well, which one do I use? Well, look at what it produces. If it produces H3O plus, then you can go to the Ka table. And if they give you benzoic acid, it should be in there. If it produces OH minus and you have benzoic acid, well, then you're going to have to be looking for the counter ion. And in that case, we wouldn't have the table for that because none of our bases have negative sign. So, but the thing is, you should look at what is produced. If it's H3O plus, look for your Ka in your Ka table, or look for the K in the Ka table. If it's OH minus, then you go to the base table. And if you don't find what you're looking for there, then come on up during the exam. I've done something wrong. Okay, now the approximation does hold. Look at that, nice. Now it's just a very simple matter of 6.3 times 10 to the minus 5 times 1.5 divided by 0.75, and X is the concentration. Now this time it's the concentration of H3O plus because there's nothing attached here. So it's 1.26 times 10 to the minus 4 molar, and the pH is 3.90. And I don't know if I did this one previously. No, I didn't. Okay, so let me just double check that. Yep, and then good. All right, and then I have one last one here. Determine the pH for a solution that is 2.44 molar ammonia and 1.17 molar ammonium chloride. Okay, so the ammonium chloride is the salt. It breaks up into ammonium ion and chloride ion. This is not going to do anything. The ammonia, when it goes into solution, it's a weak base, so it reacts with the water, produces ammonium ion and OH minus, so we know that we're going to need a Kb here. The ammonium ion breaks up 100%, so 1.17 molar ammonium chloride is also the concentration of the ammonium that will be present in your solution, and this is 2.44 molar. This is 0 minus X plus X plus X, 2.44 minus X, 1.17 plus X, X. Set it up. 1.17 plus X over 2.44 minus X is equal to the Kb, should know it by now, is because because I've done this so many times, but I still am going to double check. Yep. And then this is 2.4. Both of these numbers divided by this number is going to be greater than 100, so the approximation holds. So it should be nice and straightforward. And x is equal to 3.75 times 10 to the minus 5 molar, and that's the concentration of OH minus. I'm looking for the pH, so the pOH is 4.43, and so the pH is equal to 9.57. It's a base, it produced OH minus, the pH should be greater than 7. That does make sense. I'm going to double check. Looks good. Yep, there we go.